Hello everyone and welcome to QuantPy. We understand the HGM framework really well by now. We know it models the dynamics of the instantaneous forward rate, and we know the key to understanding the HGM is the drift condition, which we know how to derive as well. So as President Trump would put it, everything is great until you realize that the instantaneous forward rate is a theoretical construct because instantaneous borrowing really means returning the money faster than the speed of light, which is not going to happen. So you have to model something that's traded, and the LIBOR has been the most liquid market traded instrument. So it's easy to appreciate that the practitioners have been modeling the LIBOR markets in the spirit of the Black-Scholes long before the HJM framework was introduced, though you can speculate that not all of the applications would have got the drift condition right. So the development of the HJM enabled a more robust understanding of the LIBOR market models. Essentially, the LIBOR market model is a special case of the HJM framework. So we are going to tackle the LIBOR market model now. We will quickly explain the LIBOR, which will lead us to the SDE, which is the stochastic differential equation describing the dynamics of the LIBOR. We will then derive the drift condition under the forward measure and then under the spot measure, which is the equivalent of the risk-neutral measure. We will develop these concepts using a single Brownian motion to keep things simple, and we will then quickly discuss how this can be extended to multiple Brownians, which is going to be a breeze. We shall conclude by explaining how the volatility of the multidimensional LIBOR can be defined in terms of the variance-covariance matrix and how can it be decomposed in terms of volatility and correlation matrix, which are very well understood, at least conceptually, so that shall bring the LIBOR market model home. We know what a LIBOR is. It's a trim average of the estimated borrowing cost provided by a panel of banks. The rate will vary by the tenor or maturity, with the most common tenors being 3 months and 6 months. We are going to model a fixed tenor, say 3 months, so we can represent the LIBOR at time t for borrowing at time capital T for tenor equal to delta as follows. So the rate is quoted at t. We are lending the money at capital T and receiving it back with interest at capital T plus delta. The rate is published daily and represents the then cost of borrowing. So we can represent the current rate as follows. There are contracts traded on the future values of the LIBOR, such as FRAs and futures, and you can use these to construct the term structure of LIBOR. Let's assume we have generated a sequence of the current market implied LIBOR. So the second LIBOR is for borrowing at T1 and the third for borrowing at T2 and so on. As we are modeling the fixed tenor, say 3 months LIBOR, we can drop the third argument to simplify the notation. So the rates become. We shall also assume that the T's are equally spaced, with the space between them equal to the tenor of the LIBOR. Now we have to model the dynamics of these over time. For example, we can model the dynamics of a representative LIBOR as follows. For now, we assume that the randomness is coming from just one Brownian, and each LIBOR is driven by different Brownian motion, and we shall see that extension to multiple Brownian is trivial. Now, as you anticipated, we need to discuss the bank account and the zero coupon. Where would we be without the T, banks and bonds, eh? The bank account refers to investment at the prevailing rate. So we take 1 quid, invest it at the current LIBOR, and don't forget LIBOR interest amount is calculated using simple interest rate formula. Essentially, LIBOR times the day count fraction. So for a yearly tenor, the interest amount would be the rate times the balance. For a quarterly tenor, it would be balance times LIBOR times 1 divided by 4, where 4 is the number of quarters in a year. So our balance at T1 would be, and we can then reinvest this amount for another period at the then prevailing rate, and so on. We can write this generically as follows. Now for the zero coupon, we can simply write the current price of a TN maturity bond as its discounted value using the relevant LIBOR rates over its maturity. It's very similar to what we saw in the previous video. Its remaining maturity will shrink as time progresses, and at a later date, its price would be as follows. Now the value of the bank account and the price of the zero coupon are defined at the discrete dates, which are the T's, but we will be modeling them as continuous processes under the HJM framework. So how does one make them continuous? Sounds like a big challenge, but it's rather trivial to fix. Assume time progresses and we are at small t, between t2 and t3. Let I represent the time indices of our t's, and let q represent the minimum of all the future t's from that point onward. So for our small t, this would be t3. Now if we have the price of an additional zero coupon that pays 1 quid at t3, then that shall bridge the gap from current time to the start point of the first LIBOR, and this problem solved. We can write the value of the bank account at any time t with this new zero coupon as follows. So essentially, the value of the bank account at any intermediate point within an interval is equal to the value at the end of the interval times the price of the zero coupon covering the intermediate period. Similarly, we can write the price of the zero coupon at any time t as follows. Same formula as before, but we have added the adjustment for the stub period. Now our main interest is the modeling of the LIBOR, so let's try to express the LIBOR in terms of the zero coupon prices. And to facilitate that, let's write the price of the zero coupon, which matures one period later. And now if we divide the first price by the second, we get, which we can rearrange to isolate LIBOR on one side. And now we can combine the terms on the right hand side to get. And if we shift the price in the denominator to the left hand side, we can see that the expression on the left hand side represents the price of a traded asset because it's equal to a constant time the difference of two prices. So we have found a way to link the LIBOR to the prices of traded assets, and we can now infer its dynamics using the valuation formulae. We know that the price of a traded asset, expressed in the units of another asset, is a martingale on the sum probability measure. So this must hold for our LIBOR times the zero coupon of the indicated maturity. Now if we use the zero coupon of the same maturity as numeraire, then this simplifies, and we see that the LIBOR for the period between n and n plus 1 is a martingale under the probability measure induced by using the Tn plus 1 zero coupon as the numeraire. We are denoting this measure by Tn, but in some text you will see this being labeled n plus 1. It just simplifies the presentation really. And because it's a martingale, we can write its dynamics as follows. And this must be true for other maturities. For example, the LIBOR for the period between n minus 1 and n must be martingale under the measure induced by using the Tn maturity bond as the numeraire. And don't forget, we're going to be representing this measure by n minus 1. Now we can go a long way with this simple result. So we can go and price assets that depend on only one LIBOR or that can be decomposed into the sum of such instruments. For example, caplet depends on the dynamics of one LIBOR, and the cap can be decomposed into the sum of caplets, so you can price them using these dynamics. But some other instruments depend on the joint evolution of multiple LIBOR, so as in the HJM video, we need to establish the dynamics of multiple LIBOR using a single probability measure or numeraire asset. It can get complicated really quickly, so let's go one step at a time. We saw that the LIBOR covering the period between n and n plus 1 is a martingale under the measure associated with the price of the n plus 1 maturity zero coupon. Let's see what happens when we move the numeraire by one period to be the Tn maturity bond. So now the two bond prices don't cancel, Hence, the LIBOR is not a martingale under this measure, meaning it will have some drift. Let's determine the drift then. We can shift the terms to the right-hand side to isolate the LIBOR on the left-hand side. Familiar drill, right? Now, comparing this to the expectation under the Tn measure, we see that the Radon-Nikodym derivative must be as follows, which we can invert to get. Now, we saw earlier that the ratio of the two zero coupon is related to the LIBOR, and we can write this ratio at time 0. Making the substitutions, we get. Now, we need to link it to the Gersanov theorem, and an easier way to see the link is as follows. Let's denote the Radon-Nikodym by Z. We can easily calculate its differential, noting that the term in the denominator is a constant. And we can substitute the dynamics under the Tn measure. And now we can divide the differential of Z to get. Cancelling the common terms, we get. Now let's bring in the Gersanov theorem. If W is a Brownian motion under the Tn measure, and we introduce a process, then a process defined by the original Brownian minus this process will not be a Brownian motion under the original measure because we have changed the drift, right? But it will be under some different measure which we can identify via the Radon-Nikodym derivative. We can write the relationship between the two Brownians in differential form as well. Now, how do we reformat our Radon-Nikodym derivative to the form given in the Gersanov theorem? If you're familiar with stochastic exponential, this is the Dolean's dead exponential that we discuss in the Ito differential of elementary functions video, then you can easily see that the y in the Gersanov theorem must be equal to the coefficient of the Brownian on the right-hand side of our dz over z. And if you're not convinced, then just substitute this y into the expression. Then apply Ito's lemma to the log of z. Then substitute for dz over z and square to get. Now, if you integrate and exponentiate, we get the solution of z. So if you compare it to the Radon-Nikodym of the Gersanov theorem, we see that y is indeed equal to what we claimed. So we can write the relationship between the two Brownians. And now we just substitute for the Brownian under the Tn measure to get the dynamics of the Tn LIBOR under the Tn minus 1 measure. Now we can easily deduce the relationship between the Brownians under the Tn minus 1 and the Brownian under the Tn minus 2 measure. And if we substitute for the Tn minus 1, then the terms inside the brackets become, which we can write using summation notation as follows. Now to generalize, let's represent the n minus 2 by m. So this becomes. So in summary, if we use a shorter maturity bond as the numeraire, then the dynamics of the LIBOR are as follows. So the drift is positive. Now we can easily deduce what happens if we use a longer maturity bond as the numeraire. We can easily see that the Tn plus 1 Brownian will be linked to the Tn Brownian as follows. We just incremented the n by 1. So when we substitute for the Tn Brownian, the drift will be negative. Simple as that. So in summary, the dynamics of the LIBOR under the forward measure are as follows. If we use the same maturity bond as the numeraire, then the drift is 0. If you use a longer maturity bond as the numeraire, then the drift is negative. And if we use a shorter maturity bond, then you get the plus sign. So not much different from what we saw in the HJM video then. Now let's move to the spot measure. This is the equivalent of the Riis-Newton measure, by the way, which uses bank account as the numeraire. But because our bank account doesn't use continuous compounding, calling it a bank account would be slightly misleading, and that's why the alternative name spot measure is used. Let's reproduce the valuation formula. We saw that if we use the Tn plus 1 maturity bond as the numeraire, then the LIBOR would be a martingale, meaning its expected value will be equal to its current value, and the SDE will have zero drift. Now let's see what happens when we use the bank account as the numeraire. We can isolate the LIBOR on the left hand side, and remember, we can take the constant terms inside the expectation. Comparing the right hand sides of the two, we see that the two measure must be linked as follows, which we can write in terms of the Radon-Nikodym derivative. Actually, this looks very familiar and we already know the answer to this. Let's see what happens if we use the shortest maturity bond as the numeraire. So this would be the bond that bridges the gap between the small t and the start point of the first LIBOR. We can easily deduce the Radon-Nikodym derivative of this with respect to the Tn measure. Now the only difference between using the bank account as a numeraire and the shortest maturity zero coupon as the numeraire is the first ratio. We know the expression for the value of the bank account and the expression for the price of a zero coupon from our earlier discussion when we introduced these concepts. Now the bank account starts with 1, so B0 is equal to 1, which makes the first ratio easy. We can substitute 0 for small t and then calculate the ratio. Now comparing the two expressions, we see that the product terms are constant or known by time t. So the stochastic term in both of them is the price of the shortest maturity zero coupon. So the drift under the spot measure is the same as the drift under the shortest maturity zero coupon, which we already know. So we have derived the LIBOR market model drift now, but our derivation was using one Brownian. We are going to see now that it's very easy to extend it to multiple Brownians. And practice, what happens is you will be interested in horizon up to 50 or 100 years. So if you're modeling the 3 months LIBOR, you'll be modeling the dynamics of 200 to 400 LIBOR. So you can use that many Brownians if you like. For most purposes, 2 to 7 Brownians suffice. So to explain in simple settings, let's say we are modeling 3 LIBORs, which I denote by 1, 2, and 3, and we are assuming that the randomness is coming from just 2 Brownians. So each LIBOR has exposure to these 2 Brownians. By the way, the 1, 2, 3 here are just labels and they're not meant to represent the first 3 LIBORs. You can assume they're consecutive. We can write the system in matrix form as well, which is straightforward. And now you can see how easy it is to extend the number of LIBORs and Brownians. Symbols and matrices are amazing invention, aren't they? And we can write the one generic LIBOR using summation symbol as well. Now we have multiple LIBORs driven by multiple Brownians, and whenever you have multiple random variables, you expect some discussion of variance and covariance. So let's see how the variances and covariances look like. We can write the instantaneous variance of a generic SDE as follows. We know the mean is the drift term. So subtracting the mean here essentially removes the drift term, and we get, where I expanded the summation term. Since we are assuming that the 2 Brownians are independent, so we get, and that's the instantaneous variance of the dynamics of a generic LIBOR. We can now calculate the covariance between any 2 LIBORs, say I and M. Subtracting the mean inside each term removes the drift as before, so we get, since the Brownians are independent, the cross terms are 0 and each delta W squared becomes dt, so we get, and we can remove the expectation because the expected value of a constant is a constant. So we know the instantaneous variances in covariance, meaning we can generate the whole variance-covariance matrix. Essentially, the diagonal entries are coming from the first expression. For example, the first diagonal entry comes from substituting 1 for I, and the second from substituting 2, and so on. The other entries come from the second expression. For example, substituting I equal to 1 and M equal to 2 gives the entry in the first row and the second column. Substituting I equal to 3 and M equal to 2 gives the entry in the third row and the second column, and so on. So you can specify the LIBOR market model in terms of the variance-covariance matrix. We can actually do better by splitting this into variances and correlations, which again is quite straightforward. Let's take the generic LIBOR SDE and multiply and divide the summation term by the instantaneous volatility of this LIBOR. We know its variance from the equation at the top right, so the standard deviation must equal its square root. Let's represent this term by B. So the SDE becomes. Now let's apply the variance and covariance machinery to this transform SDE, just to get some more practice. We know that the variance is as follows. And we know subtracting the mean leaves just the stochastic terms. And we know the Brownians are independent, so the variance of the sum equals the sum of the variances. Now we can calculate the covariance between the I and M LIBORs. We substitute for the SDE. The drift is removed by subtracting the mean. And we know the Brownians are independent, so the cross terms are 0, and we get. And each delta W multiplied by itself is equal to dt, so we get. Now as before, we can generate the entire variance-covariance matrix by just substituting for I and M. We are almost there now. We just need to show that the B terms in the matrix are actually correlations. To see that, let's take the square of a generic B. Now each diagonal term contains an expression of this form, and it simplifies to 1. So the diagonal entries are just the variances. And each non-diagonal entry contains an expression of this form. Simplifying, we see that the numerator is the covariance term we saw before, and we know covariance divided by the two standard deviations is equal to correlation. So we can write the matrix in terms of variance and correlations. And now you can specify the LIBOR market model using variance and correlations. Right, so I hope you enjoyed the video, and I look forward to seeing you in the next.